This is your presenter Asloob Mudassar, and I am presenting slide number 119 of the course on laser physics. Question is, single longitudinal mode selection can also be achieved in a unidirectional ring resonator by placing a Faraday rotator plus a birefringent plate sandwiched between two identical linear polarizers in a laser cavity. How is the single mode operation achieved? The answer is, for homogeneously broadened transition, spatial hole burning of inversion in the active medium can be avoided using a unidirectional ring resonator. For example, the resonator shown in slide number 82 of figure 5. So let me show you that figure first in the appendix. So you can see that the caption of this figure is simple ring resonator on the left, folded ring resonator on the right. So these are the two unidirectional ring resonators, and the light will only propagate in only one direction. And using such a resonator, we can avoid spatial hole burning of the inversion, and we can maximize the output power. So these two can be used in order to maximize the output power. And these two unidirectional ring resonators can also be used in order to make a selection of a single longitudinal mode. This is what we shall explain in our main topic. And you know that here I have stated one thing, that is a spatial hole burning of inversion in the active medium. And this happens when we are using a two-directional laser cavity. That is, the light oscillates in both directions, from left to right and from right to right, from right to left. And then you know that in such a cavity, standing waves are formed, and the nodal points at the standing waves do not use the inversion, and the inversion is maximally used at the anti-nodal points. So due to that one, there is a hole burning of inversion. That is, the inversion has been used at some points drastically in comparison with the other points in the laser cavity. That is, the use up of inversion is not uniform. And due to that one, spatial hole burning of inversion is created in the active medium. So that drastically lowers the power of the laser output, and also limit some important longitudinal modes. The modes which are desirable can also be blocked by the spatial hole burning process. So in the designing, we want to avoid this spatial hole burning of inversion, and for that one, unidirectional laser cavities are recommended. So let me read again. For homogeneously broadened transition, spatial hole burning of inversion in the active medium can be avoided using unidirectional ring resonator. And you know that I have shown you the unidirectional ring resonator in the appendix, and has been mentioned in slide number 82 and figure number 5. You can consult that slide for greater detail. This then creates a possibility of single longitudinal mode selection, as discussed in the theory for homogeneously broadened laser gain profile shown in figure number 118.2. That is in the figure number 2 of a previous slide. If the laser is partly inhomogeneously broadened, the laser gain profile is very broad, and the cavity is a unidirectional ring resonator, then a single mode operation which means that a single longitudinal mode operation can still be achieved by placing an etalon or a birefringent filters in the laser cavity. As spatial hole burning of the inversion in the active medium is avoided in a unidirectional ring resonator, the inversion in the active medium is fully utilized, giving increased output power. So you see that the main objective of the unidirectional ring resonator is to avoid the hole burning in the inversion of the active medium. So once this defect is avoided, then of course we can increase the output power within the laser cavity and also outside that. And using unidirectional ring resonator, we have the possibility of obtaining only a single longitudinal modes. The other propagating modes, due to the unidirectional nature of the ring resonator, can be avoided or can be removed or suspended or attenuated. Unidirectional ring operation can be realized by using a combination of two identical polarizers with the same orientation of axis, and in between them a birefringent plate followed by a Faraday rotator is placed as shown in figure number 1. For example, this figure. The caption of the figure is, this is a unidirectional device based on the two identical polarizers, Faraday rotator and a birefringent plate. So you can see that this device is linear in the sense that all the components lie along the resonator axis. So in that sense, it is a linear device, and it can be placed in any long resonator. In any resonator having a long cavity length, this device can be placed in order to make the device to only propagate at a single longitudinal modes, because this device acts as a unidirectional device. That is, for example, as shown by the arrow, for example, like this one, the light will propagate through the polarizer 1, that is from left to right, through the polarizer 1, then through the Faraday rotator, then through the birefringent plate, and then through the polarizer 2. And when this light from the polarizer 2 is incident on the second mirror, for example mirror 2, the light is reflected back, and we shall see in the today's lecture, when the light is reflected back, the light is stopped somewhere else within this device, within this unidirectional device. So the light, except only the longitudinal modes for which we are designing this instrument, will allow the two directional propagation, and all the other devices and all the other longitudinal modes will have only one dimension, will have only one directional of propagation, that is from left to right, as shown in this figure. Then the propagation of such longitudinal modes from right to left will not be allowed. That is, such modes will be removed or attenuated or will be suspended from the cavity resonator, and will no longer be part of the laser oscillations within the cavity. The Faraday rotator contains a glass rod and an axial constant magnetic field passing through it. So you can see that this is the Faraday rotator. This is the front face of the Faraday rotator, and this is the back face of the Faraday rotator. So these are two faces of a glass rod. And you will see that there are magnets from S to N, and there are magnets from S to N, and these are the cylindrical magnets actually. And due to these cylindrical constant magnets, an axial magnetic field is produced along the direction of the resonator axis, or along the direction of the this glass rod. So now we are going to explain how the scheme will work. If a linearly polarized light with beam axis parallel to the magnetic field enters the Faraday rotator, the exit beam will have the same polarization as that of the incident beam. The polarization of the exit beam is rotated when the beam makes non-zero angle with the magnetic field direction. So you see that the polarization of the exit beam is rotated when the beam makes non-zero angle with the magnetic field direction. So you see that this is what the last sentence is, what our desired thing, that we want our polarized light to pass through the resonator in such a way that the polarization state should make some angle with the direction of the magnetic field. So it will make a non-zero angle with the magnetic field direction. So the polarization will be, so the polarization angle will be rotated when it will exit the Faraday rotator. So this is important. Assume that the axis of the polarization after passing from left to right through the Faraday rotator is rotated counterclockwise by an angle alpha when viewed by a facing observer. So you see that here we are assuming that when the light enters the Faraday rotator with an electric field of the with a polarization orientation as shown by this arrow. So when the light parallel to this one with the electric field parallel to this one is passed through the Faraday rotator, then you see that when the light will exit, we shall notice that the direction of the polarization state is rotated counterclockwise by an angle alpha. So you see that in this figure, when the rotation will take place, according to this figure, the orientation of the electric field will then be along the vertical direction as indicated by this arrow. So before entering the Faraday rotator, the electric field has this direction as shown by the arrow on the polarizer 1. So when this electric field will pass through this Faraday rotator, then after designing the parameters of the Faraday rotator, we shall see that the light will be rotated counterclockwise by an angle alpha. And here we have shown that after rotation of the angle alpha, the electric field will be oriented parallel to the vertical direction. So assume that the axis of a polarization after passing from left to right through the Faraday rotator is rotated counterclockwise by an angle alpha when viewed by a facing observer. The beam when entering the right to left will be rotated by the same angle but clockwise. So notice the difference. So when the light will be entering the Faraday rotator from left to right, it will be rotated clockwise, say by an angle alpha. And when the light will be entering the Faraday rotator while moving towards right to left, then you see that the light will be rotated, that is the polarization state of the light will be rotated by the same angle but in the clockwise direction. So from left to right, the rotation will be counterclockwise, and from right to left, the rotation of the polarization state will be clockwise. So that is why we can say that the Faraday rotator is a non-reciprocal element. That is, in the two direction it behaves differently. So it is a non-reciprocal element. Next, we describe the function of the birefringent plate. The thickness L of the plate is chosen in such a way that a linearly polarized beam entering into the plate emerges as two linearly polarized beams with pi phase difference between them. That is, the light should satisfy this equation with the 2 pi over lambda times n naught minus n times L is equal to pi, where n naught is the refractive index that the ordinary light will face, and ne is the refractive index faced by the extraordinary beam. Because the beam will split into two beams, one is called the ordinary beam, the other is called the extraordinary beam, and these two beams will respectively face these two refractive indexes, that is n naught, n in and ne respectively. while it travels the length of the plate, which is a small l. And you know that lambda is the wavelength for which we are designing this birefringent plate to be producing a phase difference equal to pi between the two beams, that is between the ordinary beam and between the extraordinary beam. So when these two beams will come out from the birefringent plate, they will have a phase difference of pi. The two pi phase shifted linearly polarized beam then combined to produce a resultant linearly polarized beam rotated by some angle, say alpha. So this is not the angle alpha, but it could be any angle. So I have said that just to say that it is an angle alpha. So let me show you the birefringent plate. You see that this is the birefringent plate, and I have shown one axis of the birefringent plate, which is the NE axis. And you see that this light from the Faraday rotator has an electric field oriented vertically in the vertical direction. You can see the arrow. So this beam, this orientation of the polarization states makes an angle alpha by 2 with the NE axis. So you see that this birefringent plate is adjusted in such a way and rotated in such a way that the beam which is incident on the birefringent plate should make an angle equal to alpha by 2 with the NE axis of the birefringent plate. So when the light will pass through this birefringent plate, it will have two polarization states, and these two polarization states will have a relative phase difference of pi according to the equation, according to our designing equation, which is given over here. Because we want to produce a phase shift of pi between over two beams. One is the extraordinary beam, the other is the ordinary beam. So that when the two such beams with a phase difference of a pi shifted linearly polarized beams are combined together to produce a resultant linearly polarized beam rotated by some angle, say alpha. So the two linearly polarized beam coming out from the birefringent plate have a relative phase shift of pi, and then when they combine together, the resultant linearly polarized light is actually a rotated version, and say that the angle of rotation is alpha. Now if an incident linearly polarized beam traveling from left to right makes an angle, say alpha by 2 with the E axis, that is the extraordinary axis of the crystal, the emergent beam as seen by a facing observer is rotated clockwise by an angle alpha. So here the rotation will be clockwise and it will be through an angle alpha, because the light which is incident on the plate, that is on the birefringent plate, if it is incident at an angle alpha by 2 with the E axis, then of course it will be rotated by an angle alpha clockwise. So it will be rotating through clockwise. Now if the beam direction is traversed if the beam direction is reversed, that is the beam is traveling from right to left, making an angle, say lambda by 2 as seen by a facing observer, the beam is also rotated clockwise by an angle alpha. So you see that through the birefringent material, if the light is traveling from left to right or from right to left, in both cases the light will be rotated by an angle alpha, provided it while entering the birefringent material, it will make an angle alpha by 2 with the E axis of the crystal. Since the rotation will always takes place in the clockwise direction, so we can say that the birefringent plate can be regarded as a reciprocal optical component. But you know that we have seen that our Faraday rotator is not a reciprocal element, but that is a non-reciprocal element because it rotates counterclockwise when the light enters from left to right, and it rotates clockwise when the light enters from right to left. Having explained the function of the Faraday rotator and the birefringent plate, the linearly polarized light from polarizer 1 is rotated counterclockwise by an angle alpha after passing through the Faraday rotator, which is then incident on the birefringent plate, oriented such that the incident beam polarization makes an angle alpha by 2 with the e-axis of the plate. The beam after the birefringent plate undergoes a rotation of alpha in the clockwise direction with respect to the incident beam. That is the beam incident on the birefringent plate. So the beam is rotated by an angle alpha when it exits the birefringent plate. The emergent beam is now identical in polarization state and sense, that is the orientation, to the beam after the polarizer 1. That is the beam after the birefringent plate will have the same polarization state as the beam has the state when it exits the polarizer 1. So as the polarizer 2 has an axis parallel to the polarizer 1, the beam will emerge out of the polarizer 2 without any power loss. So let me explain through the figure. So you see that this is the orientation of the polarization state after the light exits polarizer 1. So this electric field is incident on the Faraday rotator. The Faraday rotator will rotate it counterclockwise by an angle alpha, and suppose that the light becomes oriented, that is the polarization state is oriented vertically as shown by this arrow. And now we have arranged the birefringent plate E-axis, NE-axis in such a way that the incident beam will make an angle alpha by 2 with NE-axis. So when it makes an angle alpha by 2 with NE-axis, the rotation of the polarization states will be clockwise by an angle alpha. So this will be an exit beam from the birefringent plate, and you will notice that this exit beam has the same orientation of the polarization states as the light after the polarizer 1. So these two states are identical, and since the polarizer 1 and polarizer 2 are identical, having the same axis, so this light can easily pass through the polarizer 2 without any loss of power. And you see that this all happens for the only one wavelength, which is the wavelength lambda. And this is the wavelength that is over longitudinal mode operating at wavelength lambda, and we want this longitudinal mode to propagate within the laser cavity. And we want to remove all the other wavelengths, that is all the other lambdas, that is lambda 1, lambda 2, lambda 3, and so on. We want to remove them because we want to remove them because we do not want those longitudinal waves to propagate in the laser cavity. Only we want this longitudinal wave having a wavelength lambda to propagate within the laser cavity, because we have designed our birefringent plate according to that one. So if you are using other lambda, for example, if you are using different value of lambda over here, then of course here the phase difference will not be pi but different from pi. So the rotation of the polarization state as coming out from the birefringent plate will not be parallel to that of the state from the polarizer 1, but will making some different angle. So when this light will pass through the polarizer, the light will be attenuated because of the Malus' law, which is given by that the output intensity when the polarization states make an angle, then when this light makes an angle theta is given by I is equal to I naught cos square of theta. So you see that there will be an attenuation for such a wavelength. But when the wavelength is equal to lambda, which is over desired longitudinal mode, then of course there will be no attenuation when the light will pass through the polarizer too. Okay, you see that I have explained this paragraph also. So designing of our birefringent plate at this wavelength lambda, which is the lambda that we want to oscillate between the cavity mirrors, and this is our longitudinal mode having wavelength equal to lambda. And this setup that I have shown over here in figure number 1, actually this setup is placed in a long resonator cavity having mirror number 1 well behind the polarizer 1 and mirror number 2 well after the polarizer 2. So this is a long cavity having this as a part of that cavity. So the oscillations of the modes will take place through this cavity, and only as I shall further explain, only a single mode, longitudinal mode operating at a wavelength lambda will be passing through from left to right and also from right to left through this unidirectional device. This is a unidirectional device for all the other longitudinal modes, but this will act as a bidirectional device for only a single wavelength lambda, which is our desired longitudinal modes which we want to propagate through this cavity, and for which we have designed over birefringent plate. We have designed over birefringent plate at a value of lambda. Now, if the beam travels from right to left, so you see that I have explained in the previous paragraphs, when the light travels from polarizer 1 to the polarizer 2, what happens? What will happen at the Faraday locations, and what will happen when the light will exit the birefringent plate? And now we are talking about that once the light has passed through the polarizer 2, it will hit the mirror at the far end of at the far right end on the mirror number 2, and the light is reflected back. So when the light will be reflected back, it will be traveling from right to left. Now, if the beam travels from right to left, then the rotation of the polarization state through the birefringent plate and through the Faraday rotator will be in the same direction. That is, the birefringent plate will rotate the light in the clockwise direction, and when the light is traveling from right to left, the light will through the Faraday rotator, then the Faraday rotator will also rotate the light in the clockwise direction. So you see that when the light is traveling from right to left, then both the optical elements, that is the birefringent plate and the Faraday rotator, both will rotate the light polarization state of the light in the same direction, and in this case in the clockwise direction. And the linearly polarized beam will make a non-zero angle theta with the axis of the polarizer 1. So you see that here, since the rotation is different at the Faraday rotator, being clockwise when traveling from right to the left. So when the state, it means that the state of the polarizer, when the light will exit the Faraday rotator while traveling from right to the left, will have a state of a polarization different from the state of a polarization or from the axis of the polarizer 1. So the light will make an angle, for example, say theta, with the axis of a polarizer 1. And of course, there will be a loss of the power at that particular light traveling from right to left. So all the modes which are traveling from right to left will suffer a huge loss at the polarizer 1. So when they have a different wavelengths, for example, when the different modes are propagating at different lambdas, lambda 1, lambda 2, lambda 3, and so on, and this is the lambda that is our required longitudinal mode. And you see that for this lambda, there will be no attenuation when the light is traveling from left to right, even through the polarizer 2. But when the light is reflected back from the mirror too and traveling back traveling backward on the along the resonator axis from right to left, then of course the other modes except the mode which is operating at a wavelength lambda, the other modes will suffer a huge loss of power. For example, if the outgoing beam from the Faraday rotator towards the polarizer 1, if that makes an angle of theta is equal to pi by 2, the beam after the polarizer will be 100% lost. And if theta is not equal to pi by 2, but it is some value and differs from the polarizer axis by a few degrees, then for a low gain laser, the loss will be large, resulting in no propagation of the beam from right to left through the system shown in figure 1, except only the wavelength lambda for which we are designing our system. That will pass from right to the left also. So that only longitudinal modes will propagate between the mirrors 1 and 2 of the laser cavity. So single longitudinal mode in this way is selected. Thus, using a unidirectional ring resonator based on the system of components shown in figure number 1, the single longitudinal mode selection operation can be realized. So you see that the main use of using this in a long resonator cavity is that the power of the purpose is to enhance the power of the laser beam oscillating within the two mirrors and at the same time operating at a single longitudinal mode. So this will give you an operation at a single longitudinal mode, but due to a large length of the laser cavity with which we have with this system shown in figure number 1 acting as a part of the laser cavity will allow only a single longitudinal mode to propagate within the two mirrors of the cavity, but at the same time due to a large length of the cavity the power is enhanced. The optical power is much larger than you see in other unidirectional devices. So this unidirectional device is preferred in the sense it allows you to have a single longitudinal mode and at the same time and a very increase in optical power. So this is the end of slide number 119.